Alright, so for today's pre-lecture video, I wanted to concentrate on the idea of conservative and non-conservative forces. The reason is that it's pretty important to understand the difference between them, and I think because it's sort of a more abstract concept at some level, it doesn't hurt to have a little bit of repetition. So basically, when we're talking about forces and how they relate to the idea of the conservation of energy, we come into two types. Conservative forces allow energy to be conserved in a system. So if it's only these forces that are acting on the objects in the system and doing work on the objects, then we will find that the total amount of energy will be conserved. If we also have non-conservative forces acting on the system, then we will have the situation where the total amount of energy does not remain constant. Most of the examples that we will look at, it'll be a situation where energy is actually being lost from the system. That'll be a situation when there's something like friction acting. But you also could have work being done on the system by a non-conservative force that actually will add energy into the system. So the name of these two types of forces gives you a hint as to how they're being classified. They're being classified according to whether they allow energy to be conserved or not. So far we've actually run into two examples of conservative forces. We didn't really maybe realize it, but we did. The two kinds of forces are gravity and the force of a spring, the elastic force. So the force of gravity is mg, the elastic force is minus kx. It turns out that both of these forces have potential energy functions. The potential energy function for gravity is mgy. And for the elastic force, I know we didn't get to that yesterday, but it's 1/2 kx squared, and we will look at that in class. This is one of the characteristics of a conservative force, actually, that it does have a potential energy function. So, how do we identify conservative forces? There's a couple qualities that they have that make them conservative. One of the ones that we just mentioned is that they actually have a potential energy function associated with them. And we talk about the work done by these forces can be expressed. Remember that in last class we talked about the work done by gravity, and we were looking at that as minus mg dotted with ds. And this ended up to be minus the change in potential energy due to gravity. And so that's what they're talking about here. It also is true that the work done between 2 points by a conservative force is reversible. That means that if I went from an initial point to a final point and we did work, I could also go backwards from the final point back to the initial point, and the system would return back to its original state. It turns out that in nature, you can't always reverse a process, but with a conservative force, you can. The other thing is we're going to look at, and we'll look at this in more detail in a little bit, is that the work done is independent of the path. If you remember what this expression looked like here, it was mg y initial minus mg y final. This only depends on the initial and the final points. There's nothing in this expression that talks about what happened in between those 2 points, and that's what we mean when we say it's independent of the path. It only depends on the endpoints. And because it only depends on the endpoints, if your endpoint and starting point are the same, then the work done is going to be equal to 0. So all of these are qualities that help us identify a conservative force. So let's look a little bit more about the work done by gravity and sort of emphasize that it doesn't depend on the path. In this situation, we're imagining moving from an initial point to a final point, but we're going along this curved line. And so we are going to do look at this expression as the force of gravity times ds, because of the fact that the ds is representing the fact that it's along the path. But we can break this up into its x and y components. And so we're going to do minus mg in the y direction, and then the ds is going to be dx in the I direction and dy in the j direction, because this altogether gives us the displacement along the path. It's got a little bit of x and a little bit of y. But we know that when we take j dot I, that component is 0, so we're only going to end up with minus mg times delta y. And so in the end, the work done by the gravity is going to be actually only it's going to be mg y initial minus mg y final. And so again, what we're saying here is, notice this work done by gravity only depends on the initial and the final point. It doesn't matter. Nothing about this expression tells you that it was a curved path. So can you tell that the path was curved from this? No. You only know where you ended and where you began. And that's one of the characteristics of a conservative force, because the work done only depends on the endpoint. What we're really saying here is, for instance, if a person the gravity was doing work as the person went from this initial point to final point, you don't know if she climbed a mountain in between, if she took a straight path, or if she went through the desert valley. It doesn't matter, because it's only going to depend on where she began and where she ended. That's the characteristic of a conservative force. The other thing is that if she would have ended where she began, we would have a net work done of 0. That is another characteristic of a conservative force. So when we have work done by a conservative force, what we have found is whatever that conservative force is, when we're calculating the work, we find that it's equal to minus the change in the potential energy associated with that conservative force. We also found in Chapter 6 that the work done by a force, and this applies to any force, the net force, is equal to the change in the kinetic energy. So because if we only have conservative forces, doing work, then for a system, we can say minus the change in the potential energy is equal to the change in kinetic energy, which means that the product of these two together equals 0. Remember from class that this means that the final energy minus the initial energy is 0. And this means that we're saying that energy is equal to the sum of kinetic plus potential. Another way to state it because this means Kf minus K initial plus U final minus U initial, we can say it's equal to initial energy is equal to final energy. Both of these are ways that we can state the conservation of energy. Now, sometimes we have a force that's not conservative. Sometimes we refer to it as a dissipative force because it dissipates energy. loses energy. So let's say we have a tabletop, and there is friction on the top, and we move an object along the tabletop. Here's the initial point, and here's the final point. And we might take this path, and we might take this path, and we might take this path. A longer path gives more opportunity for friction to act. Now we know that when friction acts, that it's resisting the motion. We learned that when we learned about friction, that friction always acts opposite the direction of the motion, the force of friction. But we might not have thought about what exactly that means. We do know that it would slow something down, but think about when you rub your hands together. If you rub your hands together, there's friction between your hands, and your hands start to feel warm. And that's exactly what happens when friction acts. The energy that used to be in the system is lost to heat. And so energy actually ends up getting lost. And so the longer the path, it means more energy is lost. The change in the energy that's lost is equal to minus the frictional force times the path length. And this means definitely, in this case for this non-conservative force, that the longer this path length is, the more that the energy is lost. And so this is talking about the loss of internal energy. It's lost to heat. And so that's what happens with friction. So what we were saying here is when we have something like friction, definitely the work done, which here we really said was minus the frictional force times the path length, is definitely path dependent. And if I had moved my object around and ended up where I began, I would still have lost the energy, because all along this path the friction is acting and losing heat to the surroundings. And so it's not going to be work equal to zero like it is for a conservative force, but it will definitely be some net work done or work lost, energy lost. So that's what makes a conservative force and a non-conservative force different. So what do we do here is when we have a non-conservative force acting, we add this term right here that talks about the energy lost. And we say that this is the loss in internal energy. Sometimes I like to express it like this. Because in this case, the final energy is going to be less than the initial energy. And so this makes more sense to me to just think about it this way. But we'll talk about examples later on. So you see that this is a term that's added when we have a non-conservative force acting. When we have a conservative forces only, that term doesn't appear in the energy conservation. So sometimes I like to think of it like this. Change in kinetic plus change in potential we saw was equal to minus delta U internal. But what I'll do here is say this is just equal to minus the work done by friction. And so we see that this is a negative quantity. and this represents the change in energy over here. Because E final is less than E initial, this is negative. Delta E is less than 0 as well. And so we see that this represents the change in energy. This kind of explains where it went. But we will do some examples in class and in our homework. So hopefully this helps sort of emphasize what the difference is between conservative and non-conservative forces. We'll talk more in class, but I thought that this would be a good introduction.